Okay, our final speaker of the session, and actually today, is Samantha Lawler, who's going to speak about discoveries in the distant solar system from Classy and Lido. All right, we're just going to do a test, Samantha. Hopefully,
Okay, you can hear me?
we can hear you. Just give us one more second.
Sure.
Cool. I can't give you a wave on timing, but I'll just let you know if you go crazy over time.
Okay, sounds good.
All right.
Um, hi everybody. I'm happy to be talking to you today from Canada, where it's the National Day for Truth and Reconciliation. And I'd like to express my gratitude for getting to use the Canada-France-Hawaii telescope to do a lot of really great science from the summit of Mauna Kea, which is sacred to Indigenous Hawaiians. Um, So, where's my mouse? There we go. Okay, so I'm going to be talking about a bunch of TNO surveys. So this plot is showing area on the sky versus limiting magnitude. And the circle sizes show you kind of relatively how many TNOs were detected in all of these different surveys, right? So Rubin is going to blow everything out of the water, right? But it doesn't have a super deep limiting magnitude, right? And then there's these JWST surveys that go to crazy deep magnitudes, but they're relatively small number of detections. So I'm going to be talking about Classy and Lido, which are kind of in the middle here, at deeper magnitudes than Rubin will be able to do. So the Large Inclination Distant Object Survey was run by this fantastic group of people. We finished taking data back in 2023. We detected 148 TNOs. We looked at moderate to high inclination. We looked at two different places off ecliptic. And our goal was to get really high orbital precision to be able to diagnose resonance in these distant bodies. The Classical and Large A Solar System Survey, Classy, was a CFHT large program, so a lot more people are involved, a lot more international. We just wrapped up our last bit of observing this year, so we just have our preliminary results. Processing is happening. So this survey used the same telescope, CFHT, but using Wes Fraser's shift and stack and machine learning detection to go much deeper than we had been able to do with single exposures. And we're finding something like 150 TNOs in each of 5 fields spread around the ecliptic. And we're not going to be able to follow them up as well as with LIDO. We're still in processing. So one of our big science goals for Classy was looking at the size frequency distribution, right? So larger objects, we've been able to measure this pretty well with OSIS, a previous TNO survey. Classy has gotten us down to smaller sizes. And we're starting to see out at the kind of the edge of what we believe with Classy. It looks like the size distribution starts to roll over a bit. So that's interesting. It has interesting implications for the planetesimal formation sizes for pebble accretion. And hopefully we'll be able to tie this in with JWST results. So watch for papers on this size distribution. The second main science case for Classy is looking at distant TNO orbits. We already know that resonances are incredibly important in the distant TNO populations. And now I have to tell you a story. So most of you have seen this plot, right? So the first few high paracenter TNOs that were discovered were all on one side of the solar system. So that spawned this Planet Nine theory that there is a distant giant planet that's constraining everything to one side of the solar system. So I'm going to update this. This is from 2016. So first I have to rotate it around so that it matches my plot. So this is everything that's all the high paracenter TNOs that we know now. You can see that clustering is not as strong. There is an asymmetry still. Um, but it's been argued that only some of these distant TNOs are stable, right? So if you do a paracenter cut that kind of gets higher as you go out to larger and larger semi-major axes, sure, yeah, that could work, right? So then we have this different group of high paracenter TNOs, and when you look at those in the solar system, they're clustered. Okay, that's interesting, right? Except Kat Volk pointed out that actually a lot of these are resonant, and so they're clustered by a totally different mechanism. Kat will be talking more about distant resonances tomorrow. Let's look at this a different way. So here we have paracenter distance versus semi-major axis. This is everything as of 2019. We've got a couple more discoveries since then. We can explain all of the orbits on this plot except for these guys up here, right? The sednoids. They're not resonant. How did they get there? Those are the really interesting objects. So when we plot this again, so those are the sednoids are the purple ones, they're not clustered. And with Classy, we hope to look in a lot of different directions around the solar system and find more. Um, and so this is preliminary, but our initial, so we don't have very good orbits yet, but we have very precise distances measured for everything that we've detected so far with Classy. And there's nothing at large distances like you would expect, and that's weird and annoying. We were really hoping to find at least a couple of sednoids, but oh, we didn't find any. And that's actually kind of interesting, right? Is it a different size distribution in the sednoid population? Is it a different inclination distribution? Is there some kind of clustering happening? Rubin's not going to help us as much with this. We really do need deep targeted surveys to try to find these most distant high paracenter objects. Um, Okay, so LIDO, we focused on distant resonances. We know these are really important. More than a third of the TNOs we found are in resonance. So high inclinations, large orbits means that the resonances are super important. And right, we see this with exoplanet systems. We see this in the outer solar system. Mean motion resonances are important. One science highlight from LIDO so far is we discovered a 10 to 1 resonator, right? So Neptune goes around the sun 10 times in the amount of time this goes around the sun once. So even at really large distances, these mean motion resonances with Neptune are really dominating the structure. I can talk about some of the weird stuff that this particular object does because it's highly inclined. Ask me more. Um, but just the takeaways from Classy and Lido are that mean motion resonances are really important in the distant TNO populations. We really need to find more of these high paracenter objects to understand the past and the current state of our solar system. But this is getting harder and harder to do. Billionaires are making it harder for us to see the night sky, right? There's 8,500 Starlink satellites alone in orbit. I see them in my sky. I see them in my data. I see pieces of them falling on farmland near my house. I worry about collisions in orbit and the pollution aspect from burning up so many satellites in the atmosphere keeps me awake at night. Like this is, I know there is a lot to fight right now, but all of you astronomers are highly trained to fight this particular terrible environmental catastrophe that's unfolding in orbit. If you want to talk more about ways to fight, AAS has a really active committee. We're working for regulation of satellites. If you need more incentive, Reflect Orbital just filed to launch a mirror into orbit that it will be 4 times as bright as the full moon. We desperately need regulation in orbit, and we will have to fight for it to keep getting our measurements of the outer solar system and exoplanets. And with that, I will take questions. Sorry to end on a bummer.
All right, thank you so much for your talk. Questions? Anyone from All right, well, I'll start with a quick question, which is you mentioned JWST data, combining with JWST data. Can you actually get spectra of these objects?
I know there have been spectra taken of a few of the brighter TNOs, but the more distant ones I think are still challenging even for JWST. But that's way outside my area of expertise, so sorry.
All right, thank you. We've got a question over here.
Um, Thanks, Amanda. Excellent talk. I'm curious about this. These last couple of slides you mentioned that the satellites are a quote environmental catastrophe. Can you expand a little bit on that? Because when we look at the effect on, let's say, Rubin asteroid discoveries, we don't see anything more than a few percent. So, like, how do you reconcile those two?
Yeah, so the environmental catastrophe I'm referring to is everything that's in low Earth orbit will be burned up in the atmosphere, right? And like Starlink satellites, for example, are a ton, right? Like this is like burning up a Ford F-150. At peak operation, they'll be burning up a Ford F-150 in the upper atmosphere every hour. Right? Like they're launching many satellites and then they just throw them away. So that is at least the back of the envelope calculation, at least 8 times the natural infall rate of aluminum. We don't know what that's going to do to the upper atmosphere, right? So that's not specific to astronomy. There's lithium in these satellites that could change the opacity of the atmosphere. That could affect astronomy. Like I started talking about this because of light pollution, and I've just learned about so many other issues that are caused by so many satellites, so many throwaway satellites getting launched into orbit.
All right, we've got another question over here.
Yeah, two-part question, Sam. It's Alan Stern. First, if
Hi.
you back up, I think it's one more slide. One more before that. What caused?
Yeah.
Oops, go forward one. What
One,
caused?
this one?
Oh, in all the black dot detections, where it's highest around 110 in inclination, and it's
Oh, yeah.
5 seconds.
So, yeah.
What?
So don't put too much stock in this particular plot because this is kind of a hand wavy scattering disk model that works okay for matching the OSIS detections of the scattering disk, but definitely isn't it's not a cosmogonic model. So
So that may not be physically real. Is that what you're saying?
yeah. This is just the scattering population. We have some work to do still to actually match the orbital the orbital properties, particularly at larger semi-major axes.
Okay, thank you. And you asked us, so I'm going to ask you, what else do you want to tell us about the 10-to-1 resonator?
Sure. So most N-to-1 resonances, they librate around 180 degrees, right? But this 10-to-1 object, because it's at such high inclination, it actually also librates around zero. It goes back and forth between librating around zero and librating around 180, depending on where the argument of paracenter is. And this is really interesting behavior that we hadn't seen before. Kat Volk might talk about it a bit. Rosemary Pike has an interesting poster about other distant resonances related to this one.
Awesome. Well, let's thank Samantha again, and then all of our speakers in this session.